Welcome to the fifth lecture of week 4, where we will discuss vessel under very high pressure. So, let us start the discussion. So, if you remember the design of pressure vessel, there we have considered one standard, and that is IS 2825 code 1969. Okay. Now, what are the limitations of this code? The first limitation is that it does not give design for pressure exceeding 200 kg force per centimeter square, that is greater than 20 meganewton per meter square or approximately greater than 200 bar. And second limitation is when dO by di should be less than or equal to 1.5. So, when I am having the condition where pressure exceeds 20 meganewton per meter square, because there are so many processes in which very high pressure is dealt, or that processes will be operated, or that processes are operated at very high pressure. So, that cannot be designed while following the rules available in IS 2825 1962 code. So, for that condition we have a few examples that in which particular case pressure exceeds 20 meganewton per meter square, and very well known example is the Haber process. I hope you are getting that. So, Haber-Bosch process for making ammonia uses pressure vessel which can withstand 10 to 100 meganewton per meter square pressure, and similarly operating pressure of vessel for polythene production is 150 meganewton per meter square. So, here we have few examples where pressure exceeds beyond 20 meganewton per meter square. So, what should be the design procedure for such cases? Now, design of such vessels require failure theories. We will discuss here 4 failure theories, and based on that we will design the pressure under very high pressure. So, first theory we have is maximum principal stress theory. Next we have is maximum strain theory, and then maximum strain energy theory, and we have maximum shear stress theory. Okay. So, these theories are there to design the vessel under very high pressure, and the funny part about these theories is that while seeing the name of the theory you can find or you can identify what should be the failure condition. For example, if I am considering maximum principal stress theory, it fails, it says that my material fails when principal stresses generated or induced in the system or induced in the material is equal to principal stresses generated or induced in a simple tension test. Okay. So, what is simple tension test? For example, if I am having this wire, okay, and from both side I am applying, I am pulling it through tensile force. Okay. So, the behavior or deformation occurring in this wire will be studied, and then we can decide different properties of the material, for example, proportional limit, elastic limit, its yield points, etc. So, that is nothing but the simple tension test. So, all these theory fail occur when these particular parameter fail in simple tension test theory. Okay. So, let us start with the first theory, that is the maximum principal stress theory. So, according to this theory, failure is considered to occur when principal stress reaches to elastic limit, which is taken as yield point of the material. So, that we can obtain through simple tension test for that particular material. And here this is the expression for maximum principal stress. If you remember, this is nothing but the hoop stress, and that would be maximum at inner diameter or inner radius of the vessel, and that would be equal to sigma y, because that we are considering as yield point of the material. It is equal to pi k square plus 1 by k square minus 1. Okay. And this we have derived from this expression. If you remember, this expression we have already discussed in Lehm's analysis, but there this hoop stress is replaced with allowable stress when d is considered to di. There we have derived in terms of radius and here it is shown in terms of diameter, and further k would be equal to do by di. Okay. So, here I am having sigma y, that is nothing but the yield point where permanent failure will occur. So, this will be considered with some of the safety margin. So, considering this expression, we will design the vessel. Now, what we will design over here, if you consider the expression there, k is defined as d naught by di. So, sigma y is what? Yield point. Yield point we will consider with some safety factor, and usually safety factor exceeds 1. So, sigma y will be divided by that factor of safety, and considering this equation we will compute value of k, okay, and then either do or di will be known to me. So, next diameter I will calculate, and then difference of these diameter divided by 2 will give me the thickness of that particular vessel. Experience says that this theory is most suitable for brittle material. Brittle material means such as glass, such as ceramic and crystal, etc. Okay. So, application of this theory is better for these materials. Next, move to other theories. Second theory I am having is the maximum strain theory, and according to this, when strain set up in the material reaches the strain at the elastic limit by induced stresses, then the failure will occur, and that would be the condition for design. So, considering that, we can have the expression this, where 1 minus mu plus 1 plus mu k square divided by k square minus 1 into p will be considered as sigma y. Okay, that mu is nothing but the Poisson's ratio. And usually this theory is not good for any material. If we design the vessel using this theory, it will not give the proper results. And next theory I am having is the maximum strain energy theory. Okay. So, what is strain energy? Strain energy we can define when I am putting a load on this bar. Okay. So, when I am putting tensile load on this bar to this direction, what will happen? Elongation will take place in this bar. Okay. And that elongation is basically the strain which is occurring over here. So, once elongation takes place, it means it absorbs some of the energy, okay, and that energy is basically the strain energy. So, what is strain energy? It is the work done by this load which I am pulling in this way. It is the work done by this load on this bar in the case when energy is not going out or coming into this bar in the form of heat. So, that work we can call as strain energy. And the theory says that failure occurs when strain energy accumulated in the material is stressed up to the elastic limit. And this is the expression to design the high pressure vessel using this particular theory or to compute value of k, and this theory is most suitable for ductile materials such as steel and aluminium. Okay. So, this is basically the application of this theory, and now we will focus on fourth theory, and which is on maximum shear stress theory. According to this theory, failure occurs when the maximum shear stress equals the shear stress set up in the material at elastic limit, that is the yield point of the material. Considering this theory, we can have the design equation, and which is sigma y equal to square root 3 k square divided by k square minus 1 into pi, and then we can calculate pi from this expression also, and this theory is also suitable for ductile material, steel as well as aluminium. Okay. So, as you have seen that for ductile material we use two theories, the maximum strain energy theory and maximum shear stress theory. So, if ductile material I am using, I use both theory to calculate the thickness, and then I will choose the higher one. And further I would like to repeat that sigma y is the extreme point where failure will occur. So, we will consider slightly lesser value in design, and that would be sigma y by factor of safety. So, let us move further. Here we are discussing some of the high pressure vessel. The very common high pressure vessel is called as monoblock. Okay. So, monoblock, as you can understand, it is prepared with single sheet. Okay. So, vessels made either from thick plate, if I am using thick plate, or by forging out of ingots are known as monoblock. So, you can understand that monoblock is basically prepared with single sheet. In that case, I can consider thick plate, or that plate I can prepare by forging out ingots. So, what is ingot? Ingot means the metal bar, okay. And what is forging? I guess you understand the forging. Forging means continuous tappering or continuous hammering the hot metal. You must have seen the person who makes the instrument through iron. So, what he does? He basically heats up the iron, and then when it is heated up, he continuously hammer it to give a particular shape. So, that process is basically called as forging. So, when I am having ingot or a very thick bar of metal, after continuous hammering it, we can prepare a metal sheet from this, and then that can be used for monoblock. So, monoblock will be prepared by cold bending up to 50 mm thick plate. So, that can be easily possible. Now, how this cold bending occur? When we have the very thick metal sheet, we first roll it, okay, and when we roll it, it is done by cylinders, okay. There are 3 cylinders, one is here, second is here, and third is here. All these cylinders rolls, okay. This will roll in this direction, this will roll in this direction. So, according to the adjustment of these cylinder, we can roll the sheet, okay. So, that is done by cold bending. It means at whatever temperature sheet is available, that is at room temperature, it is simply rolled when the thickness is up to 50 mm. Further, we consider hot bending up to 175 mm thickness, and that is possible. It means up to 175 we can bend the, or we can roll the metal sheet, but for that purpose, if metal sheet is slightly heated up or it is at higher temperature, it is easy to roll. So, that is again the possible process, and above this it is increasingly difficult. It means after certain thickness, rolling of metal sheet is very complicated. So, we avoid that process. Now, what are the possibility for that? To discuss that possibility, first of all we will discuss the limitation of monoblock. And to illustrate that limitation of monoblock, we will consider maximum shear stress theory, for example. So, if you consider this theory, it says that Pi is equal to 1 by root over 3 k square minus 1 divided by k square into sigma y. Now, if you focus on this equation, what this term gives, or what should be the maximum value of this term? The maximum value of this term would be equal to 1. Okay. Now, k is basically dO by di. It means k will speak about the thickness of vessel. So, if I am considering k equal to 3, this will give 0.88 value, and if I am considering k is equal to 4, it gives 0.93 value. So, what is the point? I cannot exceed the pressure after certain limit, even if I increase the k value many folds. Okay. What is the meaning of this? If I keep on increasing the thickness, then also it will not able to sustain more pressure than the limited value, and that limited value can be decided by keeping this factor as 1. Okay. So, pressure will not increase after certain value. Okay. It means monoblock can be used up to certain pressure values, and beyond that it cannot be used. I hope I am clear. So, how I can accommodate more pressure in monoblock? Because it has the limitation. So, if I change sigma y, I can sustain some of the pressure. okay, because k square minus 1 by k square, it has the maximum value 1, it cannot go beyond this. Okay. So, sigma y value if I change, I can change certain pressure. Okay. So, that sigma y can be changed by making alloying in the material. Fine. So, in this way, let us discuss 3 different methods to construct high pressure vessel. First is by increasing yield strength of the material, that is sigma y, as I have already discussed. Second is by changing stress distribution in thick walled vessel, and this gives rise to multi-layer vessel. This is the second way, and third way is by applying both methods together. So, in these 3 ways we can make the vessel which can be operated at higher pressure than that was limited in monoblock. Okay. So, let us discuss what would be the first point, that how I can increase the yield strength of the material. Yield strength of the material can be increased by alloying the steel with chromium, molybdenum, vanadium, nickel, etc. So, by doing this we can increase the yield strength of the material. And second method is pre-stressing of thick wall vessel. As we have discussed that we should redistribute, or we should distribute the stress properly, and that can be done through pre-stressing of thick wall vessel. And this pre-stressing gives multi-layer vessel, ribbon or wire wound vessel, and coil layer vessel. So, these 3 type of vessel we can prepare using pre-stressing. In pre-stressing we basically distribute the stresses in such a way so that more pressure can be sustained in given thickness. So, what is multi-layer? That can be explained through this figure. If you see here, I am having this inner vessel, then outer vessel, then outer vessel, and then outermost vessel. So, in this way we are preparing the vessel with layers. So, what happens in the layer? When I am considering innermost layer, it means the pressure will work in this direction. Okay. However, when I am considering this layer, its pressure, the pressure at inner side of this vessel will act in this way. It means these two pressure will act opposite to each other, and then it distributes the pressure properly. Okay. So, in this way we prepare the multi-layer vessel. Now, how these layers are prepared, how these multi-layer vessels are prepared. For example, if I am having this one vessel and second layer is this. Okay. I hope you are getting it. So, what I need to do, that this vessel I will heat up, and this vessel which is falling above to this will be chilled or quenched. So, what happens when these two layers will falling to each other, to equalize the temperature it will expand because it has the heated property. Okay. So, it will expand, and this basically quench, so it will squeeze. Okay. So, therefore, both layer will sit one over another in this way. However, a small gap will be there, and therefore, pressure will be distributed in that layer, but sufficient gap will not be formed because of this process of multi-layering. So, this is the concept of multi-layer vessels. Next, I am having ribbon and wire wound. So, you can consider this is the vessel, okay, where this metal strip is wired or metal strips is rolled over this periphery, which gives strength to this vessel to sustain more pressures. And third, we have the coil layer vessel, in which if you see this image, this is basically the vessel, and around this we have the coiling, okay, and this coiling is nothing but half pipe. Okay. When we cut the pipe along the length, so half of this, if we cut the pipe along the length and then we revolve that section around this, in this way the coil layer vessel will be formed. Okay. And the advantage of these coil layering is when I need to satisfy, when I need to supply any heating or cooling media in the vessel for process purpose, these pipes will solve that purpose also. Okay. So, basically these coil layer gives stiffening to the system, and along with that it can be used as a media for heating or cooling. So, in this way we pre-stressing the vessel, and therefore it can withstand high pressure then that is limited in monoblock. And now we will discuss a few examples to illustrate design of high pressure vessel. So, here I am having example 1. A vessel with internal diameter of 250 mm is to be designed for internal pressure of 120 meganewton per meter square. Steel having a yield point of 450 is used. What I need to find is calculate the wall thickness required by 4 theories with a factor of safety as 1.5. Okay, so let us start with the solution. First theory I am having is the maximum principal stress theory, and this is the expression where this sigma y will be divided by this 1.5, that is FOS or factor of safety. Considering these parameters, we can solve this equation and find out that K would be equal to 1.53. As I know the internal diameter, I can find out outer diameter, which is 382.5 mm, and therefore thickness of vessel comes as 66.25 mm, and thickness I think you can calculate easily, that is dO by di by 2. It is simple. And next theory I am having is maximum strain theory, and that is given by this expression where mu is the Poisson's ratio and mu you can consider as 0.3. So, that sigma y by 1.5 equal to pi 1 minus mu plus 1 plus mu k square divided by k square minus 1. So, putting all values over here, I need to extract x, and that comes out as 1.63. Okay. I know the internal diameter, I can find out dO, which comes out as 407.5, and then the thickness becomes 78.75 mm. Third theory I am having is maximum strain energy theory. This is the expression. You can find out K by putting all values given over here, and K comes as 1.7, and then D naught I can find as 425 mm, and corresponding thickness is 87.5 mm. And here I am having the final theory, that is maximum shear stress theory. Expression you know already, and after solving this we can have K as 3.27, and considering internal diameter and K value, I can find outer diameter, which is 817.5 mm, and then the thickness is this. So, here I have summarized the thickness which I have computed through all 4 theories, and as steel is the ductile material, maximum strain energy theory and maximum shear stress theory are more applicable. And as steel is the ductile material which we have considered in this example, the thickness found through maximum strain energy theory and maximum shear stress theory are more applicable in such cases. So, that is for example 1. Now, I will focus on example 2. In this example, a process vessel with internal diameter of 20 centimeter is to be designed at pressure of 150 meganewton per meter square in gauge. Outside condition is atmospheric. The stress at yield point of the material is 500 meganewton per meter square, and factor of safety is 1.2. In part A, I have to find that what is the maximum operating pressure of monoblock if maximum shear stress theory is applicable. So, here basically I have to find out what is the limited pressure in monoblock. Okay. In part B, if double shell construction vessel is to be made and if the design pressure between two shells is 75 meganewton per meter square, what is the total thickness of vessel in this case? So, in part B it is double layer, so we have to find out thickness of 2 layers separately, and then we will speak on total thickness of the vessel. So, let us start the solution. Now part A says that what is the maximum operating pressure of monoblock if maximum shear stress theory is applicable. So this is the expression of maximum shear stress theory. Now what happens here, I am having sigma y which is 500. So this sigma y would be divided by factor of safety, that is FOS as 1.2, and if I am considering monoblock, it means the maximum value of this expression should be equal to 1. And further we can also consider that if k is equal to 3 or more than that, it means this factor value will not change significantly, and therefore we can calculate the limitation of p. So in this particular example, I am computing pi value for k equal to 3 and when the whole expression becomes 1. So here I am having this internal pressure 20 centimeter, pi as 150, pi I need to calculate, so I do not consider this pi. Sigma y 500 is given, so that would be divided by 1.2, and k I am considering as 3. So once I am considering k 3, this expression becomes 0.889. Okay, and maximum value of this expression can be 1. So once I am having this k square minus 1 divided by k square equal to 0.889, pi will be equal to 213.8, and when I am considering one value for this expression, pi value becomes 240.56 mega Newton per meter square. So these values of pi are basically the design pressure. Operating pressure would be 5% lesser than this. So operating pressure for both condition we can find over here, and for k equal to 3 it comes as 203.65, and for the expression equal to 1 we have 229.107. So in this way we calculate the maximum operating pressure in a monoblock. In this particular problem we are given 150, so that can be operated in monoblock. So let us move towards part B of this example. And here, as we discussed earlier, part B includes double shell construction vessel where design pressure between two layers are 75 mega Newton per meter square, and I need to find out total thickness of the vessel. So here I am having this sigma y, and here I am applying principal stress theory. So you see pi di square minus po do square divided by do square minus di square plus this expression. Okay. So for first layer, now what happens, in first layer internal pressure would be 150 mega Newton per meter square. However, pressure between two layer is given as 75 mega Newton per meter square. So for inner layer both pressure will act, 150 as inner and 75 as outer. So we will consider the expression where both pressure will be acting. It means this equation. And here we have pi as 150 and po 75, as I have already discussed. Considering this equation, we can find out k, which comes out as 1.1662, and then inner diameter is given as 0.2. I can calculate outer diameter as 0.23324, and therefore the thickness becomes 16.62 mm. Now here I am having value of DO, which will work as a reference point to determine the inner diameter of second layer. Okay. So let us start the calculation of second layer. In second layer I am having pressure 75 mega Newton per meter square. So what happens in second layer? Second layer inner side pressure is 75 mega Newton per meter square. However, outer side pressure is atmospheric only. Okay. So in gauge that would be equal to 0. So I will use this particular equation to determine thickness of second layer. Considering this expression and pi is equal to 75, I can find out k as 1.1996. Now what is di for second layer? Di I am considering as 0.24124. However, do for the first layer was 0.23324. Okay. So, 0.23324 plus 0.008 I am considering because I am assuming 4 mm gap between two layers. So, considering these values, di comes as 0.24124. So, taking di value as this, I can find out do because I know the k value, and then I can find out the thickness, which comes out as 24.076 mm. Okay. So, in this way we have calculated thickness of layer 1 and layer 2, but how I will calculate the thickness of whole vessel, because inner thickness is there, outer thickness is there, but 4 mm gap is also there. So, total thickness of the vessel becomes T1 plus T2 plus gap. Okay. So, that will come as 0.044696 meter or 45.696 mm, and that is equal to 16.62 mm plus 24.076 mm plus 4 mm. So, in this way you can find the thickness of multi-layer system. Okay. So, here we have solved two examples to illustrate how to design the vessel under very high pressure, and here I am having some of the books which you can refer. And now I will summarize this lecture, and it goes as: conditions and examples of high pressure vessels are discussed. 4 theory of elastic failure are described for design of high pressure vessel. Limitations of monoblock and ways to construct high pressure vessels are discussed, and a few worked examples with detailed solution are discussed to illustrate design of high pressure vessel. And here I am stopping lecture 5 of week 4. And it was the last lecture of this course. I hope you are benefited by the content of this course, and I wish you all the best for the upcoming exam of this course. That's all for now. Thank you.